This is Humpty Dumpty, work done with Tal Schuster, Yoav Meri, and Vitaly Shmadikov. And it's about changing word meanings. Now, the idea of changing word meanings to manipulate thought is not new, but in this context, we will talk about doing it to fool machine learning models. And machine learning models are vulnerable due to the widespread practice of transfer learning, where we take these word embeddings or vector representations of words that encode word meanings, and we use them as inputs. We learn them once, and we use them as inputs for many downstream tasks in natural language processing and information retrieval. And if we could corrupt the embeddings or literally change word meanings, then we might be able to corrupt the outputs of the task solvers. Now, this meaning that embeddings encode is learned from a public corpus that is presumably rich with semantic information, such as Wikipedia or Twitter. And this creates an opportunity for our adversary, because if meaning is learned from Wikipedia and Twitter, which are public and malleable and have many different sources that are not very properly vetted, then our attacker, Humpty Dumpty, can decide that one word means some other thing, and then poison the corpus to invoke that change in the embedding. Now, if Humpty Dumpty wants to make a targeted change in the embedding, he needs to know exactly how to modify the corpus. And this is not trivial at all, because the embeddings are learned using some gradient-based optimization procedure that is not entirely understood. And so the correspondence of corpus features with embedding distances and proximities is not very well understood. And it's not immediately clear how Humpty Dumpty would add something to the corpus and change distances in the embeddings. But what we do know is that these distances encode some notion of word meanings, and that close vectors in the embedding encode words that are close in their meaning. For example, horrible and terrible will be close in the embeddings because they are synonyms, and panda and lampan are from completely different domains, and so their meaning is totally different, and they would be far. But we don't know exactly what kind of meaning these distances encode. And we have several approaches for answering this question. One approach says that vectors of two words are close when they typically appear together, or rather when the appearance of one indicates the appearance of another. This is captured by a metric called PMI, point-wise mutual information. And there are a few analytical works that indicate the connection between PMI and vector embedding distances. Now, let's look at a few examples. So, wheels and car, they appear frequently together. The appearance of one indicates the appearance of another, so they will have high PMI, and they are close in the embedding. They are close in meaning, and that all checks out. Humpback and whale, they appear frequently together. The appearance of one indicates the appearance of another, and they are close in the embedding, so that checks out. Air condition is a little less intuitive, because while they appear together very frequently, maybe more so than humpback and whale, the appearance of one does not really that much indicate the appearance of another, because they also appear in many other different and completely different separate contexts from each other. But the PMI metric does actually capture that. So it works out well, and they have low PMI, and they are far in the embeddings. But what about the words horrible and terrible? So horrible and terrible almost never appear together in spoken language, because they are so phonetically similar that it would be awkward to use them even as synonyms. And they are synonyms. They are very close in meaning. They are almost interchangeable. And we do see that embeddings capture this similarity. So the embeddings we looked at, like word2vec and glove, do capture the fact that horrible and terrible are really close to each other, despite the fact that they have very low PMI relatively. So what this means to me is that PMI somehow misses something that the embeddings do capture, and this something is expressed well by the famous quote that you can tell a word by the company it keeps, and that words that appear together with a set of other words are similar, even if they don't appear together with each other. So if horrible and terrible don't appear together with each other that much, but they do appear together with a common set of other words, then they will be similar according to this second order proximity. And we can express the second order proximity over the corpus co-occurrences using the expression that we have for first order similarity, but aggregated over the two words neighbors. And the third approach is to use both. So we can take the expression for first order, the expression for second order, proximity and similarity, and normalize them so that they're in the same scale, and then add them together to produce the third expression. And we have indications that glove embedding distances, that's what they follow. They kind of factor in both first order and second order similarities equally. And whereas word to vec embeddings mostly follow the second order proximities or distances. And what's nice about these second order, or you can tell a word by the company it keeps type similarity, is that it works well for all embeddings that we experimented with. So glove also follows that pretty closely. So if we want to use one proximity measure for all of our attacks, we can just use second order proximity. So now we're ready to describe our attack. And the first thing that our attacker does is they want to express what they want to happen in the embedding space. So we call that the semantic objective. So they say, I want to make words closer together or further apart, or I want to introduce a new word and make it like the nearest neighbor of some other word. Then they translate their semantic objective to an objective over the corpus co-occurrences. And the corpus co-occurrences are directly linked to the training corpus. So hopefully we can get from the objective over co-occurrences to what changes need to happen in order for the co-occurrence objective to hold, and therefore the semantic objective to hold. Now, the translation of the semantic objective to the co-occurrence objective is made possible by the relationship that we found that embedding distances follow some notion of first order, some expression of first order or second order similarity. But translating or inferring the corpus changes from co-occurrence from the co-occurrence objective is not very trivial, because we still need to solve two optimization problems so as to minimize the changes that we will make to make the co-occurrence objective hold, and then thus make the semantic objective hold. And the way that this works is that we have an objective over co-occurrences, and the first optimization procedure outputs what we want to add to each of these co-occurrences in order to make the objective hold. And the second optimization procedure outputs what word sequences we need to add to the corpus in order for these additions to be made to the co-occurrences. So overall, it outputs a set of additions that if you add them, then the objective holds. Now, these optimizations have some nice properties. The second one has almost optimal performance, and the size of the resultant set is independent of the values of the co-occurrences given their size, which allows us to focus on the first optimization and optimize for co-occurrence size. And this is coincidentally, we can't really use gradient-based approaches. They're not really appropriate here, so we tailored a greedy algorithm, and I'm referring you to the paper for details. Next, we show how to attack various NLP systems, namely word-to-word translation, identity recognition, and a resume search engine. And we show that the attacks can be stealthy, so they can evade the obvious mitigation techniques that we can think about. And in the paper, we also show that they can work in a black box setting where we have very little knowledge of what the victim is doing, how they're training their model. So the attacker model parameters and the data set and everything is very different from what the victim is doing. And also the model architecture is different, and still the attacks will work. That you can see in the paper. Now we're going to attack a translation system. And the way that this translation system works is that it first maps a word from English embeddings to target language embeddings, and then it finds the nearest neighbor in the target language embeddings, and it calls that the translation. So in this case, the translation was correct. But then Humpty Dumpty can say, I want the word freedom to be really, really close to the word slavery in the English embeddings, thereby causing the word freedom to also be mapped to a really close place in the German embedding space. And what's nice about that is that it's all Humpty Dumpty did was in the English embeddings. So if it works for German, there is a high likelihood that it will also work for Spanish or any other language that uses this translation system. And so the attack is independent of the target, of even the target language, let alone the target model. So to demonstrate this attack, we made up a bunch of English words that didn't previously exist, and we tried to make them be translated to randomly chosen words in the target language. And across languages, this attack works pretty well, pretty high success rates, of course, bound by the fact that we do use the translation model and we rely on it working. So if it works less good, we will get less, the success rate of the attack will be less good. Now we're going to attack a named entity recognizer, which takes in a sentence like a tweet and extracts any named entities like a location or corporations. And we can think of systems that scan tweets for trends, and we can think that companies might want their name to be visible in tweets and be identified by these named entity recognizers that scan tweets. So Humpty Dumpty could try to fool the system by taking his completely unknown and unimportant corporation and try to force the named entity recognition system to detect it by saying Humpty Corp is really, really close to all of these corporation words, so it must be a corporation, right? You will identify it as a corporation. And Humpty can do something even more sinister, just to hurt somebody else's corporation by trying to make named entity recognition systems not identify it. So it would say Bloomberg is really far from any other corporation and it's really close to locations. So when the named entity recognition sees Bloomberg, it'll probably think that it's a location, not a corporation. And this works pretty well. So if we make corporation close to locations, it starts being identified as location versus corporation. And if we make a new made-up corporation close to other corporations, it starts being picked up by the named entity recognition system. We tried 2 models, and with both of them it worked, and the same attack for both models, which was nice. Now we have an attack on a resume search engine, and this engine works like this. There is a recruiter, and they want to recruit an iOS software engineer. So they send the query to a resume search engine, and the first thing that happens is that the query is expanded to contain the iOS and also semantically equivalent words like mobile, Android, or semantically similar words at least. And then the query is sent to or is passed through the index, and resumes that match the expanded query with all of the words are sent back. So the search engine would naturally send back resumes that contain Android experts, not just iOS experts, which seems like a desirable feature, and indeed it's implemented in many places. But it's vulnerable to our attack, because if Humpty Dumpty causes some string from their own resume, for example, their Twitter handle, to be closer to the word iOS, then what will happen is that iOS will be expanded to include the word Humpty Dumpty. And since Humpty Dumpty is also a word with a very high TF-IDF score, so see the paper for that detail, but it will not only sneakily be returned as one of the results, but it'll also be one of the first results that is returned by the search engine after this attack. This attack has a very high success rate, and up to 100% of the words we tried to insert got into the expanded query. And when that happens, Humpty's resume usually jump to the top 10 search results, and that seems like a very desirable property, especially in today's job market. It only adds a few hundred short sequences to the corpus, which seems like a minor addition that won't be detected easily. And when I say it won't be detected easily, part of what I mean is that our attack, since we add only a small amount of short sequences to the corpus, our attack does not cause spikes in word frequencies or word pair frequencies, and of course, it doesn't significantly increase the corpus size in any meaningful way because it's negligible compared to the size of the corpus. But what our attack is vulnerable to, at least our naive attack or a naive variant of the attack, is that the defense could filter out linguistically implausible sentences as judged by a language model like GPT-2. And that defense works pretty well against the unmodified attack, although it does need a clean corpus to begin with, which is kind of a chicken and egg problem. Where do you get the clean corpus if the attacker can poison the corpus? But let's ignore that for now and think about how the attacker can evade this defense. So one thing they could do is they could try to make their sentences appear likely by adding conjunctions between every two words in their sequences. And that's good. That helps the attack. It remains effective even in spite of the defense. And the second thing they could do is they could try to disguise the sequences with sequences that are already existing in the corpus. And that makes the defense filter out 70% of the corpus before it even starts being effective, and it stays ineffective even though it filters out 70% of the corpus. So that seems to completely break this defense. Now I'm referring you to the paper for more details on black box attacks, for benchmarking the possibility of editing the corpus, not just adding sentences, and for various other empirical results.